This is Unit 5 on Probability, Lesson 2, all about the addition rule. And we're going to start by talking about mutually exclusive events. So when we talk about our events, if these two events have no outcomes in common, so they have no shared outcomes, then we call them mutually exclusive events, and you will often see me abbreviate this as capital M dot capital E, just because I don't want to write out mutually exclusive every time we talk about it. So if two events are mutually exclusive, then the probability of those two events happening is 0. They have no shared outcomes, they don't happen together. If we look at the probability of A or B happening, and those events are mutually exclusive, all we have to do is add our separate probabilities, well, the probability of A plus the probability of B. Because they have no shared outcomes and they never happen together, the probability of one or the other happening is just a simple addition. So at the beginning of this unit, we played a game where we rolled 2 die, and we were trying to figure out what the sum of the 2 dice was, and if we rolled a very specific way, we won. So let's call event A, in this case, rolling a sum of 5. And event B, a separate event, is rolling 2 even numbers. So the question is, are these events mutually exclusive? So if we look at the table, all of the ways that we can roll a sum of 5, a 4 and a 1, a 3 and a 2, a 2 and a 3, and a 1 and a 4. And then all of the ways that we can roll 2 even numbers, well, we can roll a 2 and a 2. We can roll a 2 and a 4, or a 2 and a 6. We can roll a 4 and a 2, a 4 and a 4, a 4 and a 6. We can roll a 2 and a 6, a 4 and a 6, and a 6 and a 6. So if we look at our two events highlighted in those separate colors on the table, event A highlighted in purple anytime we roll a 5, and event B highlighted in red anytime we roll 2 even numbers, we would say, yes, these events are mutually exclusive. They have no shared outcomes. Because you cannot roll 2 even numbers and get a sum of 5. They have no outcomes in common. We call them mutually exclusive. So the probability of A, probability rolling a sum of 5, is 4 out of our 36 total probabilities. 36 coming from 6 rows and 6 columns. 6 times 6, 36 possible sums in the table. And then the probability of B is 9 options out of 36. 9 of the red squares highlighted. So the probability of A or B happening is 4 out of 36 plus 9 out of 36, which equals 13 out of 36, or 0.361. So the probability that we roll a sum of 5 or roll 2 even numbers in this game is 0.361, theoretically. So we're going to identify using this table if the following events are mutually exclusive, and if they're not, we're going to give an example of where they overlap. So to help us do this, I'm going to clear the table from my previous colors, and I'm going to go through and I'm going to highlight in a very similar way. So A, rolling a sum of 4, and B, maybe I shouldn't use green actually since the numbers in the table are green, B, rolling doubles. So how many ways can we roll a sum of 4? There are 3 ways. And in terms of rolling doubles, we can roll a 1 and a 1, we can roll a 2 and a 2, and we can actually stop right there because we have an overlap. So we would say these are not mutually exclusive. Rolling 2 and 2 violates these conditions. It's a sum of 4 and it rolls doubles, so they do have a shared outcome. So if we clear the table, we go back in with our highlighter, rolling an odd sum, and rolling a 3. So rolling an odd sum, there's lots of those in the table. And then rolling a 3. So we could keep going and we could go highlight across the rows and the columns for 3. But we know right away that there are already multiple overlaps. This is not mutually exclusive. And we could give any one of these examples. For example, rolling a 3 and a 2 gives us an odd sum of 5. And we end up rolling a 3 on one of our die. That's just one example. You could also say rolling a 3 and a 4, or a 3 and a 6. Any one of those violate our mutually exclusive rule. So I'll go ahead and clear the table again. And why don't you go ahead and try C and D on your own, and then go back and check it for yourself. So rolling a 4 and rolling a sum of 12. There's only one way to roll a sum of 12. And in terms of rolling a 4, we can see that there is no overlap here. So we would say these are mutually exclusive events. And there's no example that we can come up with that violates it, because there are none that violate this example. And then finally, rolling an odd number and rolling a sum of 10. So rolling a sum of 10 happens 3 different ways. Rolling an odd number is any of these columns or rows, and we can see that there is one overlap there. So it is not mutually exclusive, because we can roll a 5 and a 5. That's rolling an odd number and rolling a sum of 10. So that's mutually exclusive. So if events are mutually exclusive, all we have to do is add the probabilities together. Not too bad. So then what do we do if the probabilities are not mutually exclusive, if events do have shared outcomes? So for example, let's look at the probability of rolling doubles and the probability of rolling a sum of 6. So rolling doubles, that's 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. And there is an overlap here, because we could roll a sum of 6, and that falls within our overlap. There are other ways to roll a sum of 6, but we do have the one event of overlap. So these are not mutually exclusive, because we can roll 3 and 3. So the probability of rolling doubles is 1, 2, 3, 4, 5, 6 out of 36. The probability of rolling a sum of 6 is 1, 2, 3, 4, 5 out of 36. The probability of both of these events happening is 1 overlap out of 36. So we're going to handle the non-mutually exclusive events. We're going to start by adding. So 6 over 36 plus 5 over 36. Now the problem when they're non-mutually exclusive is that when you add your events together, you've counted this value twice because there's overlap. So in order to get rid of that, we're going to subtract it. So now we're only counting it once instead of twice. So 6 plus 5 minus 1, that is 10 out of 36. That equals 0.278. So when we have events that overlap, adding the individual probabilities is going to count it twice. So we have to subtract out one of those overlaps so it only gets counted once. This is our addition rule. So what we say is if A and B are any two events resulting from some chance process, then the probability of A or B happening equals the probability of A plus the probability of B minus the probability of A and B. Now, if A and B are mutually exclusive, then this probability of A and B equals 0. So it's really the probability of A plus the probability of B minus 0. And since the 0 doesn't do anything, subtracting 0 doesn't do anything, we have that little rule exception for mutually exclusive, but it still follows this general addition rule. You can go through the process of subtracting 0 if you want to, but we are mathematicians. We know better than that. We don't need to subtract 0 if they're mutually exclusive. So the question is, how do we know the value of the probability of A and B? That can be kind of tricky. For right now, we're going to use common sense, and we're going to create our sample space and work our way through it that way. In lesson 4, the general multiplication rule is going to help us find that mathematically later on, so we don't need to worry too much about that. So let's do some examples of the addition rule to practice. We have a deck of cards. Deck of cards is 52 cards. We're going to determine if the events are mutually exclusive and then find the probability of those events. So the probability of red, that's this half of the deck, and the probability, or the probability of a queen. There's 4 of those in a standard deck. So we can see there definitely is overlap because 2 of the queens are red. So these are not mutually exclusive. We have the queen of hearts and the queen of diamonds that violate that rule. So we're going to need the probability that we pick a red. That's 26 out of 52. Half the deck is red. The probability that we pick a queen is 4 cards out of 52. The probability that we pick a red queen, so red and queen, that's 2 cards out of the 52. So now the probability of red or queen equals 26 over 52 plus 4 over 52 minus 2 over 52. That's 28 over 52, or 0.538. So when we're looking at the sample space, we can see whether or not they overlap, and then we can apply the general addition rule. So why don't you go ahead and do B, C, and D, and then come back and check your work. Make sure you're doing it properly. So B, the probability of an ace, there's 4 aces, or the probability of a king, there's 4 kings. There is no overlap in those. So these are mutually exclusive. So the probability of an ace or a king is those separate probabilities added together. 4 out of 52 plus 4 out of 52, which equals 8 out of 52, 0.154. And by the way, if you think I'm pulling all of these decimals out of my head, I'm 100% not. Use a calculator. Don't try and do that division in your head. All right. The probability of a queen, 4 of those. Or an even number. So that's our 2s, our 4s, our 6s, our 8s, and our 10s. So we can see that there is no overlap. The queens are not even numbers, so these events are mutually exclusive. And the probability of queen or even equals 4 out of 52 plus, we have 1, 2, 3, 4, 5 sets of even numbers. 5 times 4 is 20 out of 52 cards are even. So that is 24 out of 52, or 0.462. And then finally, the probability of a black card. So that's half the deck. Or the probability of an odd numbered card. And for these purposes, not an ace. If we say odd number, we are not talking about an ace. An ace does not represent 1. It is his own card here. So odd numbers, 3, 5, 7, 9. There is definitely overlap because we've got 2 cards in each of those sets of odds that are black. So the probability of a black card is 26 out of 52. Oh, these are not mutually exclusive. You've got lots of exceptions here. The probability of an odd number is 16 out of 52. The probability of a black card and an odd card, if we take a look, we've got 1, 2, 3, 4, 5, 6, 7, 8 examples of overlap. So 8 out of 52 are black and odd. So the probability of a black or an odd number card is 26 over 52 plus 16 over 52 minus 8 over 52. And that is 34 over 52, which is 0.654. So we can work through our sample space to figure out whether or not there's any overlap. We can also do this on a frequency table. So you conducted a survey asking 600 students at school the results about whether or not they eat breakfast or don't eat breakfast regularly. And you broke down the data between male and female students. So if we select any student at random from the sample, what's the probability that the student is a female? So the probability of female, there were 278 females surveyed out of 600. So that's 0.463. The probability that someone who eats breakfast regularly, I'm going to abbreviate that just so I don't have to write it all out. If we look at breakfast regularly, that is 300 out of the 600 surveyed. That is 0.5. If we look at the probability of a female and eats breakfast regularly, now we're being more specific about which table or which cell in our table we're looking at. So female, breakfast regularly, that intersection is 110. out of 600 equals 0.183. So now if we want the probability of female or, these are not mutually exclusive, because we can see that we have one example of overlap here. So we're going to do the probability of female or breakfast regularly, and I'm just going to get even more lazy in my abbreviations, is 0.463 plus 0.5. So we're going to add the probability of female with the probability of someone who eats breakfast regularly, and we're going to subtract the overlap. So minus 0.183, and that equals 0.78. So that is lesson 2, the addition rule. Lots of different ways we can apply it in order to look at probability.